Well, thanks again for the opportunity. We're going to be talking about our case study done on the crude stabilization tower for Santos and Moomba gas plant late last year. Before going there, I would like to talk a little bit about us. We have been delivering a smart solution for asset integrity since 2017. And to do that, we have linked with the best global UT companies. Before going into details, I want to mention that in the past, we used manual UT for doing thickness tests and we call it inspection. And then when we found something and has to be doing it more routinely, we call it monitoring, but was still manual UT. With the advent of new technologies, we can now have UT permanent install monitoring sensors. If you see there, UT permanent install monitoring sensor defeat manual UT in all of the categories except for the inspection ability because it's fixed. But the way we should doing monitoring is we go and do inspection manually, and whenever we found an issue that needs monitoring, then we use the permanent install monitoring sensor. It's pointless to go manually doing that because it's a time-consuming exercise and we are not very good in repeating tasks. Plus the error is too high when we are repeating and trying to get accurate values to predict corrosion rates. So now let's get into our case. The crude stabilization tower is part of the crude stabilization plant and Moomba gas plant. It was commissioned back in 1982, so over 40 years in service. It's 33 meters high tower with a nominal wall thickness of 20 millimeters. It's made up of two main sections. Bottom is a little bit bigger with 2.3 diameter, and top, which is about half of the tower, is about 1.3 meters diameter. The function of a crude stabilization tower is remove contaminants from the crude and also lighter hydrocarbon to facilitate the storage and transport of the crude. What was the situation here? The plant wasn't shut down, so they jumped into the tower to do internal inspection and to clean out the tower and assess the condition of it. And they found that at the top of the tower, they got corrosion areas with up to 6 millimeters loss from nominal wall thickness. Okay, they did a fitness for service calculation and found to be still fit for service. Then they did a mitigation by blasting that area and putting a new coating in. And then contacted us to see how we can help them to monitor that going forward. The area where the damage were located were, as I said, at the top between train 2 and train 4. They mapped that area using phase array and grid the area and find out the lowest points and nominate those to install our sensors. So we get contacted out, and within a week we set it off one of our SmartPIMS units, which is the blue box on the right picture there, which is a corrosion erosion monitoring system powered by batteries and can be fit with a radio module with a SIM card that can send data straight away to the cloud-based software for corrosion rate calculation, NO lines, and etc. The unit was set with 8 sensors. Each of one can be calibrated and set individually. And there were 7 meters length cable from the unit to the location that we were monitoring. So as I said, within a week, we set everything and traveled to site to commissioning this unit. For commissioning, we were fit by the maps that the team prepared. So we targeted the lowest points as shown in the figure there. We run the sensors, as I said, each sensor individually. And we targeted 6 corroded areas, and 2 sensors were set as a control points into areas where the unit is still a nominal wall thickness of close to 20 millimeters. To set in the sensors, we have to jump into a dock box and into a crane to access the area and set it off, attach the sensors that were magnetically attached to there. I will now share a short video summarizing all the job that was done. after we finish the job, we present the customer with a full commissioning report where all the job that we did get documented for future traceability. So we inform the purpose of the report, the scope of work that was undertaken, how the unit was installed into the handrail and security bolting on position, and the cable running, where each sensor was installed. For instance, 1 and A are the controlling sensors, so they were onto the nominal wall thickness location put on, where the others were put on based on the map that we were provided, where we are targeting the lower points on the map that the customer provided us with. All of that were documented for future reference, so they know where we are following things in the tower. When we are commissioning, we connect it to the DCI, which is the blue box on the picture. This box here, we can connect a laptop to it and program it. So we document all that data that we use. So for instance, the shock interval of UT values is every 4 hours. The transmit interval is every 5 hours. At the time, we also do a test of data transfer to the cloud and confirm that is okay. Then we program the sensor in agreement with the client. Santos, for instance, that vessel is 20 millimeters nominal wall thickness. Then we put a warning wall thickness, which is 20 minus 3 millimeters corrosion allowance. So the warning is 17. And also Santos told us that the minimum thickness that they had calculated for that tower is 9 millimeters. So we've set that already onto the system. Then based on that, we do an initial readings, and the software is intelligent enough to highlight already items that are under the corrosion allowance. As you see, 1, 2, 3, 4, 5 of the 8 sensors were already under the corrosion allowance because they were matching the corrosion monitoring locations that the team wanted us to monitor. And the control units, the 1 and the A, are close to nominal, so they are in blue color. So this is how the system is already giving you updates. As I mentioned, each probe is independent, so we go into each probe and calibrate that out, including the A-scan signal. We set it off the gain of the signal, we set it off the start and the end of the gate, and all of that is linked to the results. In here, we show the minimum wall, the nominal wall thickness, the minimum wall thickness that we mentioned, and the warning thickness that each unit is calibrated on. That is done for the 8 probes that we're setting in this particular application. And all of that, as I said, get documented and issued to the customer as a final commissioning report. This is all that we have prepared for you. Do you have any questions?
Yeah, thanks, Nestor. It's really good. I'm familiar with the system. I just wonder, for this particular vessel, is it running at elevated temperature?
I believe it's running at 140 at the bottom, but at there it's about 70 degrees C or something.
And your equipment and the cabling are spec'd to operate at elevated temperatures. I suspect they put some insulation and cladding back over your sensors on the vessel.
That's the idea. I haven't seen that done yet, but everything is set it off that they can put it back, the cladding, covering that up, and there is no issue with that. Working at around 70 degrees is not an issue. If they would be higher temperature, then we go with stainless steel tubing going around the heat area and then continuing as a normal cable when we get out of the heat area. So that is also possible if we have to monitor something at high temperature.
Thank you.